Hi, everybody. It is VSA Online, and my name is Evgeny Oskov. So, hi. Today, I have a pleasure welcoming Nathan McDonald from Air Force Research Laboratory. And without any further delay, so Nathan, the floor is yours, please.
Okay, so thank you very much, and thank you for this opportunity to speak today. So I'm Nathan McDonald. I'm a research mathematician at the United States Air Force Research Laboratory Information Directorate, and I've been there about 15 years. Today's talk is entitled Assembling Modular Hierarchical Cognitive Map Learners for Hyperdimensional Computing. And today's talk will span two conference papers that are already on the archive and some results from a high school level challenge competition that I taught last year, teaching high school students to solve several video games using hyperdimensional computing. And I'm not going to say that all of hyperdimensional computing is so simple that a high school student could do it, but they grasped the key ideas pretty quickly and ran with it, such that we needed to add a half a dozen other games just to keep them busy that week. But it does highlight how accessible HDC VSA makes AI and ML. HDC already brings explainable AI within GRASP. Today, I want to focus on how HDC brings modularity to machine learning, further lowering the technical barrier to entry. Next slide. Standard disclaimer, I don't speak for the US government, Department of Defense, or the Air Force Research Laboratory. So by modularity, I'm looking at three different things. One is I want a module to be independently optimizable. I want a sub-goal that I can optimize towards, and then two, be able to arbitrarily configure my various modules without having to redesign or modify them in any particular way. And typically the way we're going to be able to do that is by having a consistent I/O. So that way it doesn't matter whether module 1 is the input and module 2 is the output or vice versa. For something concrete, looking at digital logic, our independently optimizable modules are Boolean logic gates. And we can have theoretical designs like a digital AND, we can have physical designs like an AND gate, and we don't care about a single NOT gate. We want to be able to reconfigure these in various ways to be able to create like a full adder. And again, the reason we're able to do this is that there's a consistent information representation. In this case, it's binary. Some of the earlier work I've done was in memristors or resistive RAM. And one of the continual problems with that is we would apply an input in voltage and get the output as a current. And that made it difficult to arbitrarily configure these things because of that mismatch. So for machine learning, deep neural networks really aren't what we want as our module. We can independently optimize them for a particular problem, but there aren't a lot of good ways to be able to take different independently trained neural networks and stitch them together to then solve a larger problem without major revisions to the neural network. And a lot of it will come from a lack of inconsistent information representation across the different neural networks, ignoring like recurrent neural networks where they're meant to be recursive. So for this talk today, I'm going to focus on cognitive map learners as a module for machine learning. This work was actually briefed earlier this year under the VSA Online. This is Christoph Stockel and Wolfgang Moss's work, and it just came out on Nature just a couple months ago. And what we're going to be doing is taking these CMLs and configuring them taking an assembly of them and configuring them together to solve. One of them is going to be the Tower of Hanoi problem. And we're going to be able to do this because we're going to use hyperdimensional computing hypervectors as our consistent input-output representation. As an aside, this was another paper that was part of VSA Online. This is Michael Hirsch from IBM Zurich with his constrained few-shot class incremental learning. And just like for digital logic, the world isn't digital, it's still analog. We need analog to digital converters as part of our digital logic suite. This was just a really cool paper, and re-envisioning our deep neural networks as a machine learning module, but as essentially an analog to digital converter, taking raw images and converting it to high dimensional prototype vectors. This unit in and of itself isn't arbitrarily configurable, doesn't have consistent input output, but it's a really important component that we'll be using, not in this talk, but going forward, this is something else we're going to want in our toolbox. So HDC and VSA proper. A lot of the fun in sitting into these lectures is to see all the different ways that people try to teach or try to introduce hyperdimensional computing. This is this particular method I'll use an awful lot. So hypervectors are really hard to get across to people. So I found that just rolling them up, they create like QR codes that it's really easy to grasp. And so when working with hyperdimensional computing, the fundamental question is how similar are A and B? And here I'm trying to represent bipolar plus minus one vectors. We don't care where the symbols differ. There isn't a most significant bit and a least significant bit, a most significant neuron or a least significant neuron. All we care about are the quantity. And so every bit, every neuron is equally insignificant. And then, of course, as we make these vectors longer, and we measure the similarity between them, and this time using cosine similarity, two arbitrary random vectors are going to have a similarity that converges to 0, such that if we measure the similarity between a pair of vectors that deviates from that, then there must be a correlation in some way. And so HDC algebra is all about the creation and manipulation and measurement of these similarities. We're going to be using the multiply, addition, and permutation set of operations. As I mentioned before, we're going to be working with our bipolar vectors using cosine similarity. Addition is going to be signed addition, where when we add all the vectors together, the result is going to be similar to each of the component vectors, much greater than 0. We'll use permutation, which is just circular shift, and that'll be very important for encoding sequences. And this is a reversible operation. For multiplication, we will also be using element-wise multiplication. And with multiplication or bundling, when we multiply elements or when we multiply vectors together and multiply vectors together, the result is not similar to any of the constituent components. However, we've chosen our multiplication operator such that it is reversible. We can query the result. And here we can ask the question, what symbol was bound with X? Multiplying W with Q, and we get commutivity and distribution, and the W's will cancel out. But we'll also get these additional terms that are not going to be similar to Q in any meaningful way. We can bundle up as noise, and so we'll get an approximate version of X. For this work, we're going to be using vectors 1,000 elements long. And so, and additionally, we've chosen our multiplication and addition such that no matter how many vectors we add or multiply together, the result is still going to be a single vector. However, the more vectors we add together, the greater the noise that we're going to incur. And so using bipolar vectors with 1,000 elements long, our noise threshold is going to be about 0.1. So, and that's what this graph is showing here, with the dashed lines indicating the max and standard deviation similarity we're going to expect for any two random vectors. So as long as our approximate X in our calculations is above the maximum noise floor, we're going to be able to apply a recovery operation such that we take our noisy vector, compare it to our dictionary of all the known vectors in our universe, and we can get back the appropriate, the correct uncorrupted vector. So cognitive map learners proper. CMLs are a collection of 3 single-layer neural networks, and the goal is to learn the topology of an abstract graph. And it can be bidirectional or directed, weighted or unweighted. For the work that we're going to show today, we're going to be working with bidirectional, so systems that with reversible operations, and we're going to use unweighted graphs. And we're going to train our neural networks to learn 3 different things. One, we're going to learn node state vectors for each of the nodes, and we're going to make these high dimensional vectors. And then we're going to learn edge action vectors. And we're also going to learn a gating adjacency matrix that says which node is connected to which node. And we're going to construct these matrices such that each column of this node state matrix is the vector for a particular node, unambiguously. And doing so means that after we've trained it, we can effectively do brain surgery on our neural networks. We can unambiguously pull out what is the vector representation for any particular node and use that for computation. So during training, we are literally training the different networks to learn node state representations such that the node state 3 vector plus the edge action 3 to 7 vector is equal to the node 7 vector. And vice versa, the node 7 vector plus the edge action vector 7 to 3 is equal to the node state 3 vector. So these actions are different vectors. And we're going to do this training using a biologically plausible delta learning rule. We're only using local knowledge. These two nodes are connected by this particular edge action. So we don't require any global knowledge of our graph. So we don't need any stochastic gradient descent. And that also means we can add or lose nodes on the fly, though we're not going to be playing with that here today. What this also means is that, and what we've shown, is that you could just generate random vectors for the node states, in this case S, and just explicitly calculate the edge actions that will satisfy those node states. So we're both allowed to learn or given some a priori node states, we can construct a CML around those, and that'll be very important later. So why bother distributing all this information and working with different neural networks to learn this sort of thing? The result is we can then, after the fact, use the CML for path planning. And that's not what we train the CML to do. We just learned local information, but then after the fact, given any starting node state, say S of t, and any target state S star, we can iteratively go through the algorithm and it will plot a near optimal path between these 2 points. This algorithm is competitive with both Dijkstra and A star, though it lacks the mathematical guarantees. But we get the path planning in real time. We don't have to wait for the algorithm to calculate the optimal path before, in this case, we're looking at robots or simulated robots anyway, before the robot makes the first step. Further, if the edge action availability changes or our target node state changes while we're calculating, we don't have to start from square one again. We can just run the algorithm right from where we currently are with respect to the new target state. So where's my mouse? There's my mouse. Showing different time steps as it goes through the algorithm. This is the symbol, the wiring diagram symbol I'm going to be using, where we have 2 inputs, our target state S star and our current state S of t. CML is the particular module, and then it's going to output the node state that the CML thinks is most useful for getting us towards the target state. And being everything is a hypervector, we can feed that back as our input state and run the algorithm recursively. So to pop the hood and go a little through the gory math, what we're going to do is take the difference between the 2 vectors, the target state and the current state. We're going to multiply that by the pseudo-inverse or the transpose of the action matrix. And that's going to result in a vector that indicates the utility score, the value of each action given our current state and where we want to go. We're then going to look at our gating matrix to say, well, given that I'm in this state, what are my legal actions? This could be a really awesome action over here, but if I'm not able to take that action, it doesn't really matter. So then next what we'll do is element-wise multiply these 2 vectors together, apply a winner-take-all algorithm, multiply that vector by our action matrix, which will produce the action state that the CML says is the best action we should take. We literally add that action plus our current state to get the next S of t plus 1. And then we rinse and repeat until the current state S of t converges close enough to our target state. And I'll highlight here, nowhere have we taught the CML what the target state ought to be. When the CML never chooses the target state, that has to be prescribed by another ML agent. And because we can perform brain surgery on that node state matrix S, we can let, no surprise, hyperdimensional computing be the machine learning algorithm that provides those target states. So the first paper is going to target the Tower of Hanoi puzzle. Tower of Hanoi is a very common puzzle where we have a system of rings on a system of pegs, and the goal is to move all the rings from one peg to one of the open pegs under the following restrictions: that we can only move a single ring at a time, and we cannot place a larger ring atop of a smaller ring. And there are a variety of recursive algorithms for solving this puzzle for any number of rings. There was also a really nice paper by Chris Elias Smith using spatial semantic pointers and a spawn architecture that implements this recursive algorithm for solving the Tower of Hanoi puzzle. We're not going to be using this Tower of Hanoi puzzle. Instead, we want to think about the actions of moving the rings in a task-agnostic manner. And so when we talk about sensors, and going back to robots, sensors observe states of being. And so I want to look at these rings and pegs system as different states of being. And given my constrictions of I can only move a single ring and only move rings on top of one another's, that sort of thing, this system has 27 legal states of being. And what I would like is to design a machine learning agent that is able to start in any legal state, legal configuration, and calculate a set of actions, a set of states that is going to allow me to get to any other legal configuration. Sensors observe so that agents can act. And that's the philosophical approach I want people to think about. We want our machine learning agent to plan how to observe a particular state. So, real quick. So we have our abstract graph. We can just apply a cognitive map learner to that. And so we can calculate our C of t, where we start with any node state t and give it our target state and let it calculate through. And if we're only interested in solving the Tower of Hanoi puzzle, going from 1, 1, 1, all the rings on peg 1, all the rings on peg 2, all the rings on peg 3, we can go between any of these corners without any difficulty. But the point of the cognitive map learner is that we could go between any pair of nodes. However, here's my mouse. However, when we task the CML for doing that, we run into some problems. And the failure case was when we ask the CML to go between points that pass one of these transition node pairs between subgraphs. And it would tend to dither back and forth between these nodes. And we expect it to be related to the high symmetry of this particular graph. And so what we did is we generated random graphs of 27 nodes, 78 edges, and asked and trained a CML for these random graphs and tasked it to calculate paths between arbitrary nodes. And it could do this 100% of the time, no problem whatsoever. So additional details in the paper, but we believe that the very particular symmetry of this graph did cause some trouble. However, what we could do to get around this is apply the sign operator to the node states of the target node states. So it converted a real valued vector from our cognitive map learner into just a binary vector. When we did that, the cognitive map learner was able to successfully plot paths between any two node states for this particular CML. But what we really, really want to be able to do is expand the system and plot something down to the very fundamental level. So say we have a collection of 7 pegs and a collection of rings, and each ring doesn't know about the other ring. Each ring doesn't know anything useful about the Tower of Hanoi puzzle. But we can allow each of the large, small, and medium ring to have unique placement rules. They can each go between ring 1, 2, and 3 without any difficulty, but maybe for the small ring, it can only get to state 6 when it's in nodes 3, or what from peg 3. If it's in peg 1, it's only then that it can get to 4 and 5, and we can allow similar for the medium ring and the large ring. Each ring CML has its own placement rules, and we can create CMLs respecting those placement rules. But then can we come along later and use these pre-trained ring CMLs to solve the Tara-Hanoi puzzle without retraining the ring CMLs and without even caring about the graphs, underlying graph structures of these ring CMLs? So first off, can we just take the raw hypervectors, node representations from the cognitive map learners and use it for hyperdimensional computing? And as computed, the node state vectors are real valued and Gaussian distribution centered at 0, so we can simply apply the sign operator to get bipolar vectors when doing hyperdimensional computing. So that's great. Further, the vectors that are the node state vectors generated from training a CML are also pseudo-orthogonal. This will not be essential, and we will have non-pseudo-orthogonal vectors in a later application, but if we can get it, their orthogonality, all the better. And again, we're going to end up with a noise floor of about 0.1 similarity. We're also going to make some modifications to our CML flow diagram that I showed earlier. And one of the things that we're going to do is using hyperdimensional computing, we get in that similarity measurement, we essentially get a spurious input detector for free. So if I get in, if the CML receives a target state and it's insufficiently similar to any of the known node states in that ring CML, in this case, similarity is less than 0.1, then the CML just ignores it. And in this case, we're going to have it output a zeros vector. So for the straight Tara-Hanoi puzzle, where in this case, we're just moving all the rings from peg 1 to peg 2. Since only a single ring moves at a time, we can construct the system as a stimulus response system. So stepping through all the different steps, we're going to note the ring that was moved, and then given the ring that was moved, what ring should move next. And we're going to note the global sequence by applying a permutation operator and the index indicating which step in the sequence. And also note real quick that, so we will take the CML vectors, our real valued vectors. When doing the calculations, we're going to apply the sign operator to make them bipolar. And then we're going to create a global policy, a monolithic policy, and then we're just going to add all these vectors together, and that becomes this policy. So during operation, in this case, the ring that we're going to move first is the S2 ring. So that'll be the current state, the current ring state, the ring that was moved most recently. We're going to take our policy, unpermute it 1, unbind the current ring state by the policy, and that will give us a noisy version of M3. That M3 hypervector will be sent as the target ring state for each of the ring CMLs. And 2 of those ring CMLs are going to ignore it as spurious input. It is no bearing to known node states in those ring CMLs. They will output 0 vectors. However, the medium ring will move, in its internal state representation, will move from state 1 to state 3. It will output that. We'll bundle all those outputs together, and that will become the next ring input, or the next current ring state. We'll unpermute the policy by 1 again and rinse and repeat. Doing this, we are able to solve the Tara-Hanoi puzzle 100% of the time for any random configuration, or for any random instantiation of ring CMLs. So this was using an external monolithic policy. We can also break this down into local ring policies, where each ring has its own policy, if this, then that, shown here. So instead of a global a global sequence, for this particular narrowly defined task, the inputs are all unique, and so we just have to apply a permutation operator on the response node, the response ring state, to be able to operate this. So as before, the diagram's a little more complicated, but we take the ring state that was the ring that was moved most recently and unbind it with each of the local instantiations of the policy, unpermute by 1, and then feed whatever value that is into our ring CMLs. Again, 2 of these are going to ignore this input as spurious, and 1 of them will change its state appropriately, and that will be fed back in. As before, we are also able to get 100% performance accuracy in implementing the Tower of Hanoi puzzle for any instantiation of these cognitive map learners without any retraining of the CMLs. But the point of invoking the CML in the first place is that we can go between any 2 points in the 27-node Tower of Hanoi puzzle state diagram. So can we take that CML and get it to task the different ring CMLs? So we have our Tower of Hanoi CML CFT, and what we're going to do is bind each of the 27 node states with a particular state of each of the ring CMLs. So on this diagram here, the first one indicates the peg of the large ring. The second number indicates the peg of the medium ring. Third number indicates the peg of the small ring. So the numbers in red indicate states where the large ring is on the first peg. So we're going to add all those node states together and then multiply that by the node state 1 of the large ring CML. We will then do the same for 2 and the same for node state 3. And then we will add these all together to create a map for the large ring. And then we're going to do the same thing for the medium ring and for the small ring. So that will create this diagram. What we have up here is the Tower of Hanoi CML, and all it sees is its graph, the triangle 27 node graph, and given a particular target state T star, it is going to calculate what the next substate needs to be. It will then just broadcast that state to each of the ring CMLs that will be unbound by each of the local maps, and that will produce a legal state for each of the appropriate ring CMLs. And they will then either move to that state or being sufficiently similar to the target state. And again, the target state can be a noisy version of that target state. So as long as it's sufficiently similar, it'll just output the correct state, the cleaned up version of that state. Using this approach, though, we're going to end up running into the noise floor. The similarity of this target state version is going to end up getting pretty close to 0.1. And so 90% of the time we are able to have the ring CMLs move to the appropriate states given the tasking from the target, the Tower of Hanoi CML. But if we apply a recovery operator and lower our noise floor threshold, we are able to recover the target state that is appropriate, and then that brings us back up to 100% path planning or tasking from the Tower of Hanoi CML to each of the ring CMLs. But what we'd really, really like is for some sort of feedback mechanism. We want the Tower of Hanoi CML to task the ring CMLs and then wait for those ring CMLs to broadcast their states back for the Tarafinoid CML to choose the next state. Kind of like, I've told you to do this, and now once you've told me you're in that state, I'm observing that state, then I can go do the next action. So what we're going to do is we're going to calculate, we're going to construct the Tarafinoid CML from the ring states of the lower level ring CMLs. So here I'm showing ring state 113, and to create the node state for the Tarafinoid, the composite Tarafinoid CML, this node state is literally the sum of the large ring state 1, medium ring state 1, and small ring state 3. And we're going to do that for each of these states. They will no longer be pseudo-orthogonal, but the cognitive map learner is still able to function perfectly. And so we can drastically simplify the wiring diagram to implement this this task. Our composite CML is going to output the target state that it needs. That is a legal input, a valid input to each of the ring CMLs. They will permute, or they will operate to get to that state, or two of them, only one of them is going to move at a time anyway, or they'll just output their current state. We add all those values together, and indeed that is a valid input to our composite CML, and we're able to run this recursively until it reaches the target state. And as hoped, we get 100% accuracy using this approach for any random states, node states for the ring CMLs. So in summary, again, why this is so cool, we've taken our problem and we've decomposed it and into different components. None of the ring CMLs know anything about the other rings. None of them know anything about the Tarafinoid puzzle. But given those CMLs prepackaged, and because we can do brain surgery on those node states, we can task them, or we can construct a Tarafinoid CML from those ring states to be able to interface with them, which is just really, really cool. So the second paper extends this a little further. This is going to be applying it towards maze navigation and sequential goal solving. So here, looking at having a simulated robot navigate variable mazes. So I'm showing a variety of mazes here. This is a 10 by 20 Cartesian grid. Each robot is able to move in the cardinal directions, north, south, east, and west. They are a set of objects that I've distributed across these mazes. There are walls creating 4 rooms. There are 5 doors, A, B, C, D, E. There is a key tile, there's a treasure chest tile, and there's a home tile. And the grid positions of the objects will change per maze instantiation, but the relative locations of objects will remain consistent. The home and key tile will always be in the leftmost room, but whether the key is north, south, east, or west of the home tile will change throughout the simulations. So the particular task we want to give our robot is to navigate from first the home tile to the key, to go from the key to the treasure, and then go from the treasure back to home. We don't care which doors it uses so long as it does that, and it can't hit walls. This is a difficult task if you're going to just train a single deep neural network to solve, for a variety of reasons. One, the objects keep moving. And that's a problem because information gets slurried together. We need to be able to do both strategic level planning and tactical level planning, where how do I want to go from point A to point B, and then how do I actually get from point A to point B, especially as I have doors, walls and doors that keep moving. And then as another example, which we'll get into, is, well, what happens if a door is locked, suddenly unavailable? Well, how do I take my neural network? How do I tactically edit the neural network to accommodate that new piece of information? So unsurprisingly, we're going to be applying cognitive map learners to address this problem. And we're going to create two. One to do strategic level planning. That's going to note object relationships. And the other one's going to do tactical level planning. And it's going to it's going to tell the robot how to navigate a 2D grid. And then we're going to get these two CMLs to talk to each other via hyperdimensional computing. And we will implement this tasking of objects just using a behavioral policy and just adding vectors together. So our grid position CML, what we're going to train the robot to do is just plan paths over an empty 2D grid. And because of the high symmetry, that means that we can actually simplify our CML. And that particularly we can simplify the action matrix and the adjacency G matrix. In this case, for a blank 2D grid, every node can do the same 4 actions excepting the edges. They can go north, south, east, and west, which means that I can just shrink my A. Instead of 780 something unique edge actions, I can just make it 4. And that also means that I don't need a unique gating matrix or entry for each node state. All the gating adjacency matrix was for was to say which actions are legal actions. Well, here an action is only legal if I can't hit a wall. So what we can do is replace the gating matrix with a set of 4 touch sensors. And that will give me the same information about whether a particular action is legal or not. And to highlight again modularity, I had my CML. I know exactly where to edit my wiring diagram. I just have to edit my G matrix. I just have to apply a new input here, and nothing else has to change after the fact. I've already trained my CML. I don't have to change anything else, just editing very particular pieces, and then we're off to the races. However, the position CML is not sufficient in and of itself. If we just let it run, what'll often happen is it'll dither along the wall. It doesn't know where anything is. It doesn't know that there's a door below it that it just needs to get to be able to get into the next room. So what we're going to do is create an object CML. The object positions are relatively invariant, so we can just create a graph related to that where nodes represent objects and edges denote line of sight. It's an unimpeded line of sight. You could incorporate Euclidean distances as the weight would be 1 over that Euclidean distance, but it involves a little more work, and so we didn't incorporate that today, but that is an option. And just some of the examples of the plots that it'll give, it'll tell you how to go through the various doors to be able to get to the various objects. So now that we got our 2 CMLs, how do we get them to talk to one another? And again, we can do that brain surgery. Literally what we're going to do is per maze. So let's start again. We've trained up our object CML. We've trained up our grid position CML. That gets done once. We can do it multiple times if we want, but you only have to do that once. Each maze is unique. And so we need to create a unique map for that maze, but that's it. And so all we're going to do is multiply the particular object by its particular node state on the grid position CML. More details in the paper. There are some quirks with node state positions in a grid CML. Little complicated, but that's more or less what needs to go on. We then add all those values together, and then we can query it after the fact. I want to get to the treasure, unbind the treasure vector with the map, and we'll get an approximate version of the particular point we want to get to. All right, so now that we've got all our CMLs, we've got our policy, go from the home to the key to the treasure back to home, and our map. How does the robot run? So we're going to unpermute our policy. That'll give us our particular target object. We're going to feed that to our object CML. In this case, we always start at the home tile. So that's our current state. The first object is going to be the key, so it's going to tell us that we need to go to the key. We're then going to ask, well, where is the key in this maze? We unbind the key with the map, and we'll get an approximate version of its position. We're then going to clean it up. We're going to recover what that exact position is. So there were 200 node states for the grid, and like I said, there were some complications. So we ended up just making a sub-dictionary of here are all the positions for the objects that we care about. A little easier to clean up, and we're able to get the perfect position of that key. We then feed the key position to our grid CML, and using our touch sensor to navigate the walls, and we just run it recursively and let the action tell the robot, does it go north, south, east, or west? Now, at each time step or robot action, we're going to take that position, query it of the map. Is there any object that resides at that spot? And until it gets to the objects that we know about, there better not be anything. But then once, and again, because we care, or because of the spurious input detector, the object CML is going to ignore spurious inputs until we actually hit the key. Once we get the key, once we are at the key tile, have the key object recovered from the map, feed that to our object CML, unbind the policy, and we step through the rest of the policy to be able to navigate the maze. And highlight again, modularity. We have our grid position CML, we have our object CML, and we can put our dashed line, says we can make that as its own module. Every new maze, the only thing we have to change is this map over here. Everything else stays the same. So some additional results. So again, going from home to key to the treasure, showing that there's variation in the paths that the robot takes to navigate these different mazes. And this is due to just the variations in the random vectors that were generated at any given time. There's also variation in the way back. So even though the robot used the same set of doors, D and B, to go there and back again, it follows a different trajectory. The CML, the collection of CMLs, is not memorizing a path. It is tactically planning out where it needs to go at every time step. And over here, it's even taking different doors to go backwards. So we get a lot of variation in behavior for free. And then going back, sorry, I lost my mouse. Going back to the opening illustration where what happens if we locked a door. Here's our CML collections. How do we edit this to account for that there's a missing door? So the object CML is what encodes whether an object is accessible or not, whether there was a valid line of sight. So we can just open the hood, go back to our G matrix and zero out the elements that say that there are valid paths to that door, close everything back up, and run the CML. And indeed, here is when all the doors are available, and then running the robot through the maze with the obstructed door, we get different paths. And all of that falls out very, very cleanly. So MedArcade, so 2 papers, and then lastly, I wanted to talk about every year the Air Force Research Labs Information Directorate, in collaboration with the Griffiths Institute, hosts a week-long challenge competition for area high school students for scholarship. And I was asked to come up with a challenge problem, and thought hyperdimensional computing would be really, really awesome to give to high school students. High risk, high reward. They either get it and are awesome, or very, very frustrated for a whole week. So this is some of the ways that I was trying to get across. I taglined it. It's machine learning algebra with QR codes. For the simplest aspects, it's just high school algebra. We can add, we can multiply. We're not going to get into complex numbers, but more or less that's what's going on. And if you understand how to write equations for that, you can, for the students, you can write equations, you can write computer code to be able to do this. And one of the tool suites that we were playing with was this Meta Arcade. This came out of Johns Hopkins University Applied Physics Lab, and this was designed for recurrent reinforcement learning algorithms. And one of the things that they were addressing is that for like the Atari games, all the Atari games are different. So are you really showing that your neural network is learning how to take the elements from one game and apply them to another game? So this is a suite of games where the framework is all the same. There are only 5 actions, there are only so many elements, they have walls. And we had them break these problems down to and write the equations as hyperdimensional computing such that they could kind of like the Matrix, I know Kung Fu, when they get to a new game, they could take their bag of parts and add it to the robot to be able to solve the different games. So this is one of the earliest papers I read in hyperdimensional computing, and you should recognize a few of the authors there. And they were looking at honeybee concept learning, but it was a very simple, here is a set of sensor values, and we're going to pair that, we're going to bind that with an action. And so that's our scene is our sensor values. We're going to bind it with an action to create a scenario. And our policy, our experience is the bundling, the addition of all those scenarios. And then, and the students were, their task was to figure out what sensors they needed, how many scenarios they needed, and then we would let it play the game. We would encode the game based on the scene, the set of sensors that they came up with, and then or unbind that with their experience, cleaned up the action, and the robot performed the action. And they did that for each of the games individually. And then I said, but now you need to be able to add all those experiences together such that the robot could play all the different games. And that took them a little bit of thought. But like I said, by Tuesday afternoon, we had to give them more games because they'd already figured out how to do all of that. So it is a very, very powerful tool, even for something simple like this. And as I'm quickly running out of time, I won't belabor the point, but this is just a quick example for an example game, Avalanche, where they have the little puck down here, and these 2 bars mean they can move left and right, and they need to catch the different blocks. And so they have a variety of sensors, the displacement sensors, the block to the left or to the right. Is it a good block or a bad block? There were blocks that could kill them. Could you shoot the blocks? And then what side, player left, player right, and that was for a couple particular games. So for this particular game, they only needed the displacement sensor. And there are really only 2 or 3 scenes that you really need to describe this game, whether the block is to the left, right above you, or to the right, and then you could multiply those with particular operations, add them together, and then that's your policy. But then if you're playing Invasion, it's very similar, except now you need to shoot them. So how would you update your scene? What sensors do you incorporate and your policy? What could you update to accommodate that? So to wrap all this up, modularity is really big for machine learning. I think for making it more accessible, or just lowering that technical threshold. Nobody wants to program in C unless they absolutely have to. Everyone wants to program in Python. You're really abstracting how into the weeds you really need to be. So cognitive map learners as just a really powerful machine learning module, independently optimizable, but by making those state vectors hypervectors, we're able to start assembling them in an arbitrary way to solve larger problems. Again, because our consistent information representation are those hypervectors. Moving forward, I did mention, and this just really is a cool paper, Hirsch's with their constrained few-shot class incremental learning. Up to now, everything I've described for hypervectors, they're just generated out of the ether. But we really want to be able to apply this in the wild. you could use this type of framework to generate prototype vectors that we could use as the node states for the cognitive map learners. CMLs accommodate both just learning arbitrary vectors, node state vectors as well, and they can accommodate when I prescribe the vector. So a lot of flexibility there. So want to do a formal paper on the MetaArcade, and MiniGrid is another reinforcement learning suite that's out there, and would like to play with that, would like to apply the cognitive app learners further, or instead of just a node representing a item, maybe that node state represents a whole behavioral policy or an experience vector from that MetaArcade game. And we based, if we can identify what game we're in, we're actually going to change what behavioral policy we query. And with that, thank you very much.
Nathan, thank you very much for your talk. Thank you, indeed. So let's see if we have questions. At least we have one comment from Josh. He says that that's very cool. That's yeah, but
yeah, that was in reference to the project with the high schoolers. I thought that was pretty neat.
Yeah.
Yeah, that was a lot of fun.
Very interesting topic.
Mohsen?
Thank you.
Yeah. I think I'll follow on a couple of stuff with you. So I think my student they got some questions too. So they text me. So yeah, really interesting.
Sounds good.
Nathan, maybe I have one question to you. So again, so I probably need to read more carefully the paper. But this architecture with CMLs that you presented, at least visually, so it resembles this resonator network somehow. Is there any similarities more than visual, or it's just phantom that I have?
No, visual. I probably stole the wiring diagram from that resonator paper as a visual cue. You do involve the transpose. You do involve things like that, and that can be used to the mathematics. Yeah, there are going to be some similarities for the mathematics, but it's not the same thing.
Then for follow, yeah, okay, yeah, I presume so. Another question I had that the sign. So, what's the nature of the improvements that you get by binarizing, and why it doesn't work with the real valued vectors?
So, let's go. Use my mouse. So I do want to. I do CMLs. You can't. I'm not showing any of the work, but you certainly can do the CMLs in complex numbers. And at some point, I'd prefer to work using the FHRR or something along those lines. But for simplicity, just use the map for the binary vectors. So as I'm assuming the question is in reference to why the Tara Fanoy CML only worked for the sign vectors.
Mm-hmm.
That I don't know offhand. That is, and I haven't spent the time to really run that to ground, because at some point, cosine similarity shouldn't care about amplitude. That's the point, and it's all the sign is doing is operators is doing is just setting the amplitudes to plus minus one instead of the real value. So I'm not entirely certain why that is.
Mm-hmm.
We also had the same difficulty when we did that composite CML, where we added the node states of the rings together to create the same CML, but with the non-orthogonal vectors. That also had the same failure case of the dithering at the nodes. So really do think that it's a function of the symmetry in the graph. There are a couple tricks I'd like to apply to try to break that symmetry, but I just haven't sat down long enough to do that.
Okay. So let's see if others have questions. Please unmute yourself and speak up. All right. Looks like everything is crystal clear. Well, yeah. Well, anyway, so I guess we always have a possibility to ask questions offline. So, and I look at my clock, so time is running up. So maybe it's good time to wrap this talk up. So if I would like to thank you once again, Nathan, for the great talk. And so in 2 weeks from now, we will have the concluding webinar of VSA Online. So we will, which will feature 2 shorter talks. So please keep in mind and see you in 2 weeks from now. Thank you all for coming.
Thank you very much.
Thank you. Bye-bye.